That's good. What is mysterious submission? Right.
So welcome everybody for the final CAM colloquium of the semester. I did the rounds over in the next group. I guess everybody has, we've got a complete quorum of people who are here. So the last speaker, last but not least, is Sam Wang, who has been in the Department of Statistics and Data Science since 2021. So this is his second year as an assistant professor here. Before that, he spent some time at the Booth School at University of Chicago as a postdoc, and before that was a PhD student at University of Washington. And before that was at Rice as an applied math undergrad. So his application area tends to be social sciences, but he does a wide variety of interesting stuff in statistics with causal models and uncertainty quantification and mixture models and a few other things. And mostly I've interacted with him in non-technical contexts so far, and so I'm looking forward to seeing this talk as well. With that, I'll hand it over to Sam.
All right. Thanks, Dave. So appreciate you coming out here. I know it's the end of the semester, everyone's busy, so yeah, excited to be able to talk to you about some recent/ongoing work. So before I jump in, just want to point out this is joint work with Juan Kohler, who's at the University of Chicago, and Matthias Durden, who is at TU Munich. All right, so today I'm going to talk to you about the problem of learning causal models from observational data, and in particular how we might quantify uncertainty when we learn causal models. But before I jump in, I want to give you a little bit of motivation as to why you might want to learn the causal model. So we live in this kind of age of big data where we have often enough samples to build incredibly complex predictive models. And in a lot of cases, these models are very sophisticated and give us really good predictions from really these black box models. Okay, and so you might be asking the question, I think it's a valid question, if we can get really good predictions, why do I actually care about causality? Okay. So I think that there is some sort of intrinsic satisfaction in learning causality, right? And one might argue that this is all of science is about learning causality. But beyond that, I think one of the main kind of selling points for learning a causal model is that it allows you to reason about interventions or when you make changes onto the state of the world. So let me give you a small toy example here. So this is a figure from the New England Journal of Medicine in 2012. Each of these points on the chart represents a specific country. On the horizontal axis, I have the chocolate consumption per capita, and on the vertical axis, I have Nobel Prizes per capita. Okay? So there's actually a quite high correlation, right? It's 0.791, it's very statistically significant. And if you were to use one of these variables to predict the other, you could actually get a good, good predictions. Okay, so say you show this chart to Martha Pollack, and she asks you, well, should I then, she's interested in increasing research productivity, should I then start handing out free chocolate to everyone on campus?
Yes.
Right? This is not a bad outcome, right? Or perhaps you're an executive at Hershey's, right? Should you start funding basic research so that we win more Nobel Prizes and increase the chocolate consumption in the US? Right? Both of these questions are interventions onto the current state of the world, right? And so without a causal model, we can't really answer these hard-hitting questions. All right, so as most of you probably know, kind of the gold standard for learning causality or learning causal relations is a randomized control trial, right? So we want to do RCTs, but oftentimes these randomized control trials, they can be really expensive. They could be unethical, or we might just not have the technology to do these things. So I would argue that learning causal relations from observational data is still a really important tool for advancing science and generating hypotheses. Yeah.
I don't want to spoil your punchline if you're planning to come back to this, but can you tell us what they were using this figure for in the article?
Yeah. I think it's pretty tongue-in-cheek. It's not. This is Meserly, the author here. I don't think is actually advocating for any specific chocolate-based policy.
No, I mean, my interpretation is, some latent variable
Yeah.
representing overall wealth of the country that Collins was hoping that.
That's what I would conjecture as well. Yeah. But we would need a causal model to establish. Okay, so let me give you a more serious example, right, of where you might actually want to draw causal conclusions from observational data. Okay, so this is now kind of in the causal discovery world, this is now kind of a classic example of a protein regulatory network from a paper by Sachs et al., which appeared in Science in 2005. Okay. So this is a representation of how proteins might interact within a cell. And you can see there are directed edges in this graph, and each of these vertices here represent specific proteins. So in this kind of representation, what this graph here means is that we have, for instance, this protein, PLC gamma, and there's a directed edge pointing towards PIP2, which is another protein. And so this encodes the idea that PLC gamma has a causal effect on PIP2. And I'll kind of formalize this in a little bit, but I just want to use this as a running example as we go through. Okay, so in the paper, this is called the consensus network, and what that means is that there were a lot of experiments done, likely by grad students sitting on a bench somewhere, and this was kind of, this specific figure was the coalescence of a lot of experiments and a lot of papers that kind of established that this is the ground truth of what is happening in the cell. This is a long, tedious, expensive process, and so this is exactly the kind of area which we would hope we might be able to use causal discovery tools to help us get at least a good guess as to what the causal model is without having to do as many experiments and randomized control trials as we might have done in this case. Okay, so today I'm going to be talking to you about the problem of causal discovery, which is exactly this process, by which I mean the problem of estimating causal structure or selecting a causal model from data which typically is observation. Okay, so throughout this talk I'm going to be using the language of graphical models, and in particular we use a graph to represent some sort of complex system. And in this graph, each of the variables, or each of the nodes, in this graph represents a variable that I might observe in my system. And the edges in my graph represent some sort of dependence relation between the variables. In particular, if, say, node P has a direct effect on C, then I will put in a directed edge from P to C, and I will say that P is a parent of its child C. If there exists a directed path from, say, node A to node D, we'll say that A is an ancestor of the descendant D. And we're going to assume that the true model corresponds to an acyclic graph. And by acyclic, what I mean is that you can't start at one node, follow a series of directed edges, and get back to that same node. So for instance, in this example here, there's an edge from y1 to y3. So this would represent a direct causal relationship from y1 onto y3. So we would say that 1 is a parent of 3. There's a directed path that goes from y1 to y3 to y4. So we would say that y1 is an ancestor of y4. So when we assume that the graph is acyclic, this implies that there is a valid causal ordering. And what I mean by a causal ordering is that I take some permutation of the nodes, theta, and theta u is less than theta v only if u is not a descendant of v. So kind of put another way, nodes which appear later in the causal ordering do not have a causal effect on nodes which appear earlier in the causal ordering. Okay. And so I'm going to just define a little bit of notation here. PA of V, DE of V, AN of D of V, and ND of V are going to denote the parents descendants, ancestors, and non-descendants of people. And then when I have an ordering, specific ordering that I'm thinking about theta, I'll use PR theta of V to denote the nodes which precede V in the order. Okay, so there's a little bit of notation on this slide. I'll go back as we go through, and I'll try to clarify as we go along. But are there any questions before I jump into some of the other material?
Just about what you mean by edge, you said that it's like it implies that like y1 causes like y3, for example.
Yep.
Like concretely, like what do you mean by that? Like does it mean like given y1, like the distribution of y3 is different, or yeah, what's that exactly?
Yes. So broadly speaking, yes, and I'll give you some specific examples in a few slides.
Does the word causal mean that there's some sort of like time-like dependence involved, or?
There can be, but not necessarily. Yeah. So causality is you know, if you think too hard about it, it gets very philosophical, and yeah, this is. I will give you a formal model for what I mean here, and we'll stick to the mathematical model. But I agree that there's a lot of kind of philosophical implications that I'm not going to talk about today. All right. Okay, so I told you I'm going to talk to you about causal discovery, which is the problem of learning causal models from observational data. And this is a very broad topic, but generally the place where people start is the question of identification. So what I mean by this is, what do I need to assume so that I can pick out the correct causal model, and correct, you know, maybe in scare quotes here, given population values. Right? So if I were to observe an infinite amount of data, could I determine what the right causal model is? Right? So the secret to proving stronger theorems, right? So the secret to identification is making stronger assumptions, right? So the game that people play here is, can I assume a class of models that is small enough so that the causal structure can be identified, but is large enough to reflect the true process. Right? So there's this tension between what you can identify and kind of how close the model is to what is happening in the real world. Okay, so let's just say for now that you can identify the causal model, and I'll show you an example of what I mean by this in a little bit. But the next natural question is, if I can identify the causal model from population data, can I identify the model given samples? Right? So under various assumptions, how can I consistently recover the causal model from sample data? So there's a lot of procedures here that have been designed and proposed, and a lot of these procedures have shown to be consistent. So under the right assumptions, as n goes to infinity, you get the right causal model with probability going to 1. But generally, these procedures take in data, and what they do is they just output a single point estimate of the causal structure. And this is where most procedures stop, right? At least from a frequentist perspective. Okay, so I'm a statistician, right? So we're all about point estimates, but point estimates aren't generally good enough, right? Statisticians are often very concerned about how we might quantify uncertainty. And so that's what I want to talk to you about today. So the question of uncertainty is, how much confidence do we have in the estimated causal structure, right? So if you give me a set of data, I use this data, I estimate a causal model, the estimated structure can be incorrect because of sample variability, right? It could be incorrect because I've made the wrong assumptions, or I have a misspecified model, or often it could be both, right? So these are questions that, as I'm using these causal discovery procedures, that I want to be able to know about the point estimate that I have. Okay, so this is what the talk will be about for today. So I ultimately want to talk about uncertainty in the causal model selection procedure. All right, so perhaps the notion of uncertainty over model selection is maybe a little bit unnatural, right? So it might not be kind of something that you have thought about before. So let's think about something where we think about uncertainty quite a bit, right? So I'm going to run a linear regression This is something that you might have seen in some stats class somewhere, right? And I'm going to get linear coefficients estimated from my data, and I want to form a confidence interval around these linear coefficients. Okay, so we know how to do this. We have kind of software that does this for us. But broadly speaking, what are the questions that we're trying to answer when we form this confidence interval? I'd argue kind of broadly speaking that there's maybe at least two questions. The first of being, how trustworthy is my point estimate? Okay, and this is a little bit of a vague term, but you can think of some notion of trustworthiness. And then the second question that you might answer, right, is, or you might want an answer to, is what other possibilities are not ruled out by my data? So for instance, if you run a linear regression and kind of avoid it, if your confidence interval that you get for this coefficient is very wide, you might think that your point estimate is not very trustworthy, right? And so this, I'm kind of ignoring kind of issues of the scaling of the data and things like that, but you might be less confident about your point estimate if the confidence interval is very wide. And you might also look into your confidence interval and see what other points are in there, what are other possibilities that are not ruled out by my data. Okay, so we're going to try to do that, but for the causal model setting. There is a little bit of work that has been done in this area, but most of these procedures, or I should say all of these procedures, consider specific edges or parameters in my causal model, and they ask whether or not, or they test whether or not those edges are present. But kind of the big thing that they all assume, the crucial assumption is that you can recover a causal ordering from your data. And so if you know a causal ordering, then you can test whether there's a specific edge, but you have to know the causal ordering first. So what I want to talk about today is the problem where we consider uncertainty over the entire causal structure. And this is essentially kind of valid even when the causal ordering cannot be consistently recovered. Okay, so I'm going to propose a framework for producing confidence sets for causal orderings. And I'll tell you exactly what we mean by that in a little bit. Are there any questions before I, yeah?
So basically, what is the difference between the causal ordering and the edges in the graph? I thought the causal ordering was the edges in the graph.
Yeah, so the edges, okay. Good question. So here, there are, in this graph, a valid causal ordering would be 2, 1, 3, 4, or 1, 2, 3, 4. So it's just an ordering of the nodes, edges, or the ordering of the nodes, but there doesn't necessarily imply an edge from everything that comes before to everything that comes after.
Just that going in that direction. Okay.
Mm-hmm. Yep.
Thanks.
Okay. Okay, so before I dive into the procedure, let me discuss the type of models that we'll be considering. So before I mentioned that we require various assumptions in order to identify causal structure, right? And so let me show you one of these examples one of the types of models that we might assume to identify causal structure. In particular, we're going to assume the linear structural equation model setup. So if I observe a vector y, I'm going to assume that each element, which I'll denote by yv, is a linear function of its parents in the graph, plus some idiosyncratic error term. Okay, so these are models that are used quite often in the social sciences, and increasingly popular in biology and neuroscience and other areas as well. So one of the crucial assumptions I'm going to make here is that these idiosyncratic error terms, epsilon v and epsilon u, are mutually independent. Right? And so you can think of this in some ways as encoding the assumption that I have observed all relevant variables to my system. Right? There's no unobserved confounding happening. Okay, so it turns out, under this assumption, under this assumed model, I can recover the exact graph which generated my data from population values when the error terms are non-Gaussian. Okay, and so I want to make a kind of a quick note here. The linearity is not crucial here. We can relax this to be some sort of additive model, but I'm going to stick with the linear model here just for kind of for clarity. Yeah.
So this distributional assumption about the errors, is it important that they're not Gaussian, or is it simply that you can solve this problem for a wider class of errors than just Gaussian errors?
So it is critical that they are non-Gaussian.
This is an evolution problem, right?
Yes.
So that's right there.
Okay.
Thank you. So let me. So I've told you, right? We typically want to assume things are Gaussian, right? This is typically we're scared of non-Gaussian data, right? So if you haven't seen this before, this might seem like a little bit of science fiction, right? If we assume something is non-Gaussian, somehow this gives us actually good results. So let me give you a little bit of intuition here for why this happens. Okay, so I have a bivariate sample here. I have two variables, which I'm going to call P and C. And in particular, C is a linear function of P, and the error terms are uniform distributions with variance 1. Okay, so the true graph is that there's an edge, directed edge from P to C. Okay, so what I've done here in both of these plots, I'm going to test two models. I'm going to test whether there's an edge from P to C, or if the edge goes actually in the opposite direction from C to P. So I want to know which one's the cause, which one's the effect. I can plot out the data on both sides. I've plotted what I think is the child, or I think is the cause, or the parent on the horizontal axis, and I've plotted what I think is the child on the vertical axis. Right? So here, basically, you can just think of these as just rotated copies of each other. Okay? So on the left-hand side, I've correctly specified the model. On the right-hand side, I've incorrectly specified the model. Okay, so I fit a linear regression in both cases where I regress the child onto the parent. Okay, this seems like, if I think there's a linear model going on, this seems like a natural thing to do. And I can plot that out in red. Okay, so far, it's pretty hard to distinguish between these two charts, right? Okay, so now what I can do is I can plot not the child on the vertical axis, but I can plot actually the residuals from my regression. On the left-hand side, where I've correctly specified the model, you can see that the residuals are independent of the regressor, or the parent. On the right-hand side, we see that the residuals are uncorrelated with the parent, right? This comes from the first order conditions of least squares. But in non-Gaussian models, and this is where non-Gaussianity really is key, uncorrelatedness does not imply independence. And so in fact, we can see that the residuals are still dependent with the regressors, or the parent, because as you kind of go through different values of what I thought was the parent, you can see that the support of the residuals changes.
Question, if the epsilons had univariate Gaussians but not a joint multivariate Gaussian, would you still have identifiability?
I don't think so. I'd have to think about that.
Because you were saying zero correlation implies independence if it's jointly Gaussian, but it doesn't
If they're, yeah. So in general, yeah, I'd have to think about that. So the types of statements that we make, and I'm not going to go into these details, but the types of statements that we make are statements that you can identify the graph kind of for generic parameters, right? And so I'm going to be very hand-wavy about this. So there are specific examples where you have non-Gaussian data and you can't identify the parameters, but these are somehow, if you think about a class of models, these are essentially measure zero in some like very hand-wavy vague sense.
But to follow up, do we ever, like on the previous slide, the way you find, I'm just trying to, is ever the joint distribution, does it appear? in the deconvolution problem, if you go in the previous slide, like, we assume a model, not this, right there. Not just to I don't know, David, do we care about the joints? In other words, well,
Yes.
of course, the joint of EV, but epsilon V, but not any pair of errors that could be even more joint in Gaussian, if you know what I'm saying. So in other words,
If there's one Gaussian and
no,
others
what
are
I'm trying to
non-Gaussian.
say is that epsilon V needs to be independent of epsilon U. So let me just see, and they need to be jointly over V and U. I'm answering my own question, non-Gaussian.
That's right.
Over V and U. So in other words, like the big joint should be non-Gaussian.
Yes.
If it's big, I mean, this is one node at a time. I'm just imagining that we do multivariate
Wow.
response. But that's a little, that gets hairier and
So-
it's
so
not as
this-
elegant as this is.
Yeah, this-
Right. Yeah.
Well, the characterization is a little bit complex because you can some of these can be Gaussian, and you can allow essentially you can allow one of them to be Gaussian,
Okay, right, that's.
but they cannot be jointly Gaussian.
Yeah, okay, thank you.
Now that I look at your second assumption, univariate Gaussian does apply multivariate Gaussian, because you're assuming not just uncorrelated, but actually independent, right? That's a double bar there, so you're assuming independence?
Right. Yeah.
Yeah, so I guess,
So for any
That
pairs,
answers my question.
any pair need to be jointly non-Gaussian, that's what we are saying.
Yes.
yeah.
Okay,
Okay.
but they can be jointly non-Gaussian in many ways, and you say that once in a while you can allow for one epsilon, for one
One marginal to be Gaussian. Yep.
Right, but which is in some sense irrelevant if you look at the joint, because, yeah, okay,
Yep. Yep.
yes, thank you.
So this is a problem.
We're catching up. We're
Okay,
catching
okay.
up.
So if you've seen the ICA problem,
Yeah,
independent
yeah,
component analysis,
exactly. That's
this
what
is
that's exactly-
essentially
That's what I'm
yes.
trying to get to. Right.
Yeah. So the ICA problem essentially boils down to something
Yeah.
like this.
And is Gaussian or non-Gaussianity required even in the nonlinear case?
So no. So this is actually something like that happens. There are pathological examples that are not identified, but in general, you can allow epsilon to be Gaussian, non-Gaussian, and you can take pretty general forms of FFE. So you need kind of essentially the PDF of epsilon has to not cancel in some like
Yeah.
very specific way with
Exactly.
the second derivatives of FE. Okay, great. So
Can I, just a very naive question, since you flashed back through there. What would that look like if it were Gaussian for the intuition?
I don't think I have the slides. I have shown these slides in previous talks. Both of them would look essentially like kind of the basic.
I see, they would just look like Gaussian ellipses.
In both cases. Okay, so this intuition that I showed you for the bivariate case basically holds for the multivariate case, right? And so this slide is not exactly correct, but I think the intuition is captured here, right? So say I have a node V and some other set U. I'm going to regress V onto U, and I'm going to get those residuals, and I'm going to call those residuals eta V set minus U. Okay, so suppose I'm doing this at least in the population setting. So eta VU is YV minus some, you can think of this as the least squares, maybe estimator, and minus YU. Okay, so the standing intuition that I showed you on the previous slide holds here. If the set U contains the parents of V, so if it contains the direct causes of V, and it does not contain a descendant of V, so it does not contain a set, it does not contain a variable which V has a cause on, then the residuals will be independent of the regressors. So this same kind of graphic that I showed you on the previous slide also holds in the multivariate case. However, if I include something that does have, if I do include a descendant of V into the set U, then generally the residuals will not be independent of the regressors. Right? So take kind of this intuition that I showed you in the bivariate case, and basically it holds in the multivariate case where now I'm not just regressing the child onto a single node, but I'm regressing it onto a set. Okay, so this is what's not quite true, but roughly speaking, this condition that the set U contains the parents of V, but does not contain any descendants of V, or is contained within the non-descendants of V, another way to say this, is approximately equivalent to this independence criterion. Right? So I can check whether the residuals are independent of the regressors. Okay, so this is how you might identify a causal ordering. You would go through and you could, if you didn't care about computation, you could just go find the largest set U, such that when you regress V onto U, that the residuals are still independent of the regressors. And this tells you this gives you enough information to order or to get a causal order. Okay. Are there any questions?
I'm unclear how I get the ordering. That's always been my question. When I have many, right? I mean, I don't know if two comes before one. So I decided this guy's U, right? Comes before something else, or whatever the notation
Yep,
is.
U comes before
U comes before V. But within U, I mean, like, and then, okay, so that's important that U as a whole comes before V, but if I care of how things in U connect, or what's the causal ordering within U, I'm not understanding how I cover it from here.
So roughly speaking, you could do this in iterative way. So you can find a leaf,
Okay.
and then once you have,
yeah.
and then you
I
repeat.
see what you mean. Oh, as simple as that.
Yep.
If I didn't care about computation.
That's right. That's
Okay.
right. And in fact, you can. So you don't have to. If you were to do this in an iterative way, it's still kind of p squared, right? Where p is the number of variables, because you're doing this essentially p times, and each time you consider kind of p candidates.
What's the not quite part of the not quite true statement at the bottom?
Yeah. So it can be that this part doesn't hold. You can regress V onto something that's smaller than the set of parents, and this independence can still hold.
I see. So the condition on the left is not quite necessary for the condition on the right.
Right.
I see.
Yeah.
Thank you.
But under certain kind of it's
We mostly encounter situations where it is necessary, so to speak.
Under further assumption.
Under further assumptions.
Okay, sure.
Yeah, I'm happy to document that.
Okay.
Okay, so as I described to Flory, there's a way that you can estimate the causal ordering. Once you have a causal ordering, we have a linear model. You can do some sort of variable selection procedure, right? We know how to do, if you have a linear model, we know how to select the variables. You can do whatever you want, and this gives you the graph. Okay. So if you do this model selection procedure, you get a single graph. But as I told you, right, like there are many ways that many reasons why this graph you might select might be wrong. Perhaps your assumptions are incorrect, or perhaps you just didn't, there's sample variability, and so any number of reasons why you might not have a lot of confidence in your select graph. So what I want to propose is a specific way to get uncertainty over these causal graphs. And in particular, it's a relatively straightforward and simple way to do this. And so here's the general strategy. For a given causal ordering theta, suppose I have some sort of goodness of fit test so that I can test whether the causal model holds for this causal order. Okay, so for now, just assume that I have this.
I don't interrupt, I just want to have it clear in my head. For me, theta is a set. The causal ordering is 1375.
Yes.
Is this what we are talking about?
Yes.
Theta is a set.
It's an permutation. It's an order.
It's an order, but in the set, that's what we are talking about throughout, whenever we talk about this, okay?
That's right.
Okay, so because it would be interesting to see the test statistic
Yeah.
for that set, for the things.
Yeah. So you can, or you can. I often kind of maybe use it as a map from a set to itself.
Okay.
As a
Yeah,
permutation.
exactly, sure, okay, sure, perfect, okay.
So say I have a goodness of fit test for this causal ordering, right? One way to get a confidence set that kind of looks like a confidence interval is to simply invert this test. And so what I mean by invert this test is that I can test an ordering theta, and if it is not rejected by some level alpha hypothesis test, then I'm going to include it in my set. Right? And so, so I test the causal ordering, get a p-value pi theta. I include theta in my confidence set theta hat if the p-value is larger than some user-specified alpha. Okay, so why is this an object that you should be interested in? Right, so the question of that we talked about for confidence intervals, how trustworthy is my point estimate, and what other possibilities are not ruled out by my data, have an answer in this object. So for instance, when I ask the question, how trustworthy is my point estimate, if theta hat is very large, this means that many orderings cannot be ruled out by kind of the signal in your data, and so that the estimated ordering may be unreliable. The second question, what other possibilities which are not ruled out by my data, right? This is exactly the set theta hat. And then the question of, well, are my assumptions valid? Right, I've assumed a linear structural equation model. Is this true in practice? Maybe, right? And so theta hat also gives you an answer towards this, right? And it says, if theta hat is empty, we know that there are no orderings which satisfy the identifying assumptions, and you might want to use different identifying assumptions to estimate your causal model. Okay, are there any questions about theta hat? How much time do I have? Okay. Okay, so there's a few slight kind of complications that I want to discuss about this object, right? So there may not be a single causal ordering, right? The example that I showed you at the beginning, there were two valid causal orderings. And so if I let theta g be the set of all valid causal orderings, when the goodness of fit test is asymptotically valid for any theta in theta g, then I have something like, in the limit, theta hat, the intersection of theta hat and theta is non-empty with some user-specified probability. So if you have a unique causal ordering, theta hat is, theta g is equal to 1, and then you can actually make some sort of inclusion statement here. But when there are multiple causal orderings, this is kind of the statement that you can make. Okay, so we focus on causal orderings largely for computational reasons, which I'll discuss in a little bit. But if you are given the true causal ordering, and from that causal ordering you can estimate the graph consistently, then you can make a statement that you might otherwise might seem a little bit more natural, that the graph that you, the true graph was within some sort of estimated graph set with some user-specified probability. But for now, we're just going to kind of focus on the causal orderings for computational reasons. Okay, what are other reasons why you might be interested in theta hat? It gives you what I'll call a conservative set of ancestral relations. So if I think about the set script A here, which is the pair of nodes U and V, such that U is an ancestor of V, right? So we're saying all the causal relations in this set, U has a causal effect. It might not be a direct effect, it might be a downstream effect. But there's an effect from U to V. I can form this set A hat, which essentially looks through all of the causal orderings in my set theta hat, and then I can make some sort of statement here, which the estimated, it's conservative in the sense that this might not contain all the ancestors, but I will be very sure about the ancestors that I posit. And so the A hat is within the true set of ancestors with some user-specified probability. So this is similar, if you've seen this 2016 paper by Jonas Peters, which is about invariant causal prediction, they have a similar notion of ancestral, conservative ancestral sets in there. Okay, and then I'm going to skip over this slide in the interest of time, but I'm going to tell you that you can also estimate causal effects, so direct causal effects that are not conditioned on getting the right graph, but you can form confidence intervals that are valid over the model selection procedure. Okay, so theta hat, hopefully I've convinced you this is an object that you care about. This is an object that you would like to compute if you can. But there are significant statistical and computational problems in order to get this object. So let me tell you about my problems. Okay, are there any questions before I dive into this? Okay. Yeah. I go very briefly over it, but I think there'll be some things that are interesting. Okay, so recall that the way that we were able to certify kind of an ancestral relation was by this regression procedure and then checking the independence of the residuals and the regressor. So I think I was careful in describing the previous procedure to say that we were doing this in the population setting. And if you do have population data, then this is actually the way that you would do this is just to naively do your regression and then test for independence, right? So you can use whatever independence test you want to use. There's a lot of these non-parametric independence tests. Pick your favorite one, and you can use that. Okay, so a naive kind of when I have actual data, a naive way to do this is just to do this with the data. Regress YV onto some set of nodes that precede it in your ordering. You get the residuals, eta hat. Here I've used hat because these are the estimated residuals because they come from the estimated linear coefficients. And then I'm going to test this independence of eta hat and its predecessors. Unfortunately, in this case, the linear coefficients that we are trying to estimate, they're nuisance parameters. And so even when the null hypothesis is true, because I've estimated this linear coefficient here, the residuals that I have are actually the true kind of residuals plus some sort of error term, which comes from the fact that I don't have the true linear coefficients. Okay, so here, eta hat contains something that is independent of the regressors plus some term that is actually the regressors themselves. So even in the null hypothesis, it's not true that the residuals that I would form are independent of the regressors. So if you pick your favorite independence test, if it has kind of the right amount of power, right, to detect against local alternatives, this test will not be valid for testing the causal order. Okay, so that's the statistical problem. Okay, so what I want to say is that there have been a couple of other works that address the issue of testing the linear model, the goodness of fit test for a linear model, by looking at the independence of the residuals and the regressors. And they think about this specific problem where the linear coefficients are a nuisance parameter, and they get around this in a couple of different ways. What I'll say is you can use any of those procedures that have been previously proposed. We have a specific procedure which has, we think, nice statistical properties for our setting. It is also, importantly, very computationally inexpensive. And I'm gonna, sorry Flora, I'm gonna gloss over a little of the details here, but we use a residual bootstrap we have some test statistic which is you can think of this as the correlation between a nonlinear function of the regressors and the residuals. And this is going to be something like my test statistic, and I'm going to calibrate the distribution through a residual bootstrap. I do want to point out that there are a number of other works that do something quite similar, or not do something similar, but they address a similar problem. Like I said, you could use those as well. We think our specific example, or specific procedure is well suited for our problem, but yeah, I'm not going to say that it's better in all circumstances. Okay, so this this residual bootstrap procedure that I described allows me to test for a specific V, specific node in my set, and a specific and the predecessors, whether the causal ordering that I specified for that specific node is valid. Okay. So to test the entire ordering, I'm going to just do this for every single node in my ordering, and then I'm going to combine my test statistics into a single value, until I'm going to aggregate them in some ways. And the way that I'm going to aggregate them is I'm going to take the minimum p-value across all of my variables. Okay, so for each variable, I've done a goodness of fit test. This gives me a p-value, and then I'm going to do this for every variable, and then I'm going to take the minimum of those p-values. Okay, what we can show is that the p-values that you get from each of these individual tests are asymptotically independent. So under the null hypothesis, we can compare them to the minimum of uniforms. Okay, so this allows us, if they were not dependent, we would need to use maybe some sort of Bonferroni or some sort of multiple testing correction. But because they are independent, we can use something that's maybe a little bit more powerful when we are calibrating a null distribution. Okay, so very concretely, what does this look like? So say that I have the ordering 1, 2, 3, 4. What I'm going to do is I'm going to test, I'm going to regress y2 onto y1. I'm going to get the residuals eta 2, and I'm going to test whether they're independent of y1. Again, we can't do this directly, but we're going to use this residual bootstrap procedure, which I didn't really describe, but happy to talk to you about this afterwards. And then this is going to produce some p-value that comes from the independence test, and we're going to call this gamma theta 2. I'm going to go down the line. I'm going to look at y3. I'm going to regress it onto y1 and y2. I'm going to get the residuals. I'm going to test whether it's independent of y1 and 2. And then I'm going to produce another p-value. I'm going to go all the way down the line. I'm going to take the minimum of these p-values, and I'm going to compare it to the quantiles of a beta 1,3, which happen to be the distribution of the minimum of uniforms. Once I do this, this gives me a final p-value, which I'm going to denote pi theta. Okay. Any questions about that?
I do have a question, but it's not about this. It's about what about doing something else. So
Yes,
no,
but I would
that's
be happy
not-
to talk about this.
Exactly.
Yes.
Not now.
Okay, so what can we show about this procedure? Basically, we can show that it does the right thing. We have, for an individual, for a specific ordering theta, we can show that we have, that this test is asymptotically valid if the elements of epsilon truly are mutually independent, right? This is what we assumed in our model, and the errors are sub-exponential. Okay, we can show this as long as p, the number of variables that I have, p log p over n goes to 0. So we're not assuming any sparsity here. We're just thinking about a causal ordering, so I need to kind of let P over N go to 0. And if theta is consistent with my graph, right, if theta is a good causal ordering, the bootstrap distribution that I told you about, how we calibrate the null distribution using a residual bootstrap, converges in Wasserstein to the true distribution, and everything works out. So, okay, I told you this also works in the nonlinear setting. You can see this theorem works in the nonlinear setting as well, under additional assumptions. Okay, so those are the statistical issues. So what I'm going to do, right, naively, is I'm going to take every possible ordering, and I'm going to test it. And then I'm just going to include all the orderings in my set theta hat, which are not rejected by my goodness of fit test. Right? So when P is moderately sized, this is a lot of orderings, right? This is P factorial orderings. This becomes very, this is just an intrinsic computational barrier to this particular approach. But we can do a few things to hopefully, not in the worst case scenario, but in practice, we can do a few things which speed up computation. And in particular, right, one of the things that I said is we're going to test each of the variables one by one. We're going to test down the line. I'm going to look at the first node of my ordering, the second node, so on and so on. And then I'm going to take at the end, I'm going to take the minimum is my test statistic, and I'm going to compare it to the quantiles of a beta. Okay, so if I'm taking the minimum p-value across a number of tests, I actually don't have to go all the way down. I can stop once I have a p-value that is below my threshold, and I don't have to test the rest. Okay, so this means that I can stop early and I don't have to test the entire order. So that's nice. And if I'm clever about how I do each of these tests, I can do basically a branch and bound procedure which doesn't, which avoids redundant computation for other orderings. So I'm going to test all orderings of size 2. I'm going to rule out some of these. I'm going to test all orderings of size 3 that are not rejected, and so on and so on. So this is like this allows me to avoid redundant computation. So I'm not going to look you in the face and tell you that this is a computationally fast or procedure, right? I'm going to see you all around campus. I would not tell you that, right? And be able to see you later, right? But what I can tell you is that this is feasible, at least in simulations. On a single core, we can get up to size of graphs of size roughly 13 to 15. Right. And you can parallelize this, so if you're a little bit faster, you can go a little bit further, but I do want to be clear that this is an intrinsic limitation to what I'm telling you. I have until 45, sorry. Okay, so let me show you some simulations. We're going to consider the linear structural equation model setup. I'm going to let P equal to 8. So this is not a huge graph, but there are in the figure that I showed you at the beginning, this Sachs et al. Data, I think there were 12 variables in there. So this is not so far from settings that people are interested in. Okay, so I'm going to generate a linear structural equation model. I'm going to think about drawing errors from different distributions just to kind of see and compare how these work. The first thing that you might ask is, I have this set theta hat, which I told you contains the causal orderings with some user-specified probability, right? So this is like a 95% confidence interval. And I guess in this case, we created a 90% confidence set. So this is what the empirical coverage is for n equals 500, 1,000, 2,500, 5,000. So the punchline here is that indeed, for reasonable sizes, even at n equals 500 for p equals 8, which is in some ways it's not unreasonable size of data for the set of nodes, we can get a confidence interval that indeed gives us the right coverage. Okay, so we have the right coverage, right? But if I gave you a confidence set that included all orderings, right, that would also have the right coverage. So is the confidence set that I'm producing, is this informative? Right, so informative depends on, right, so if I have a smaller confidence set that contains the causal orderings, then this is what I want, right? So here what we can see is, again on the horizontal axis I have sample size, on the vertical axis I have the proportion of orderings in my confidence set. Right, so there's 8 factorial orderings. How many of them are still left in my confidence set for any given sample size? We can see that as the sample size grows, the confidence set shrinks down, right? And this is what you'd expect over a confidence interval. If you're doing this for a scalar value parameter, you'd expect as your sample size grows, your confidence interval shrinks down. I do want to point out one kind of thing here. So these are in the solid lines. I've shown you the proportion of orderings in the confidence set. These dotted lines show you the proportion of times that a causal discovery procedure, kind of the state-of-the-art causal discovery procedure, gets the right causal ordering. So I've kind of specifically designed the simulations so that you can see that these lines are roughly flat as n increases. So I've kind of scaled down the signal as appropriately with the sample size, so that we're in a regime where we actually cannot consistently recover the causal graph, but we can see here that still the confidence set that we are producing shrinks. So this is kind of the case where other kind of, if you're testing a specific parameter, they have required that essentially these dotted lines go up to 1. And we're saying that even in this case where they don't, we can still get something that's a little bit informative.
That's impressive, I should say, you know?
Well, you tune a little of these simulation settings and, you know.
Oh, okay, well, I was gonna say, it's very impressive. Do we have a sharper theory that goes with the simulation? Is there a characterization
Of the power?
I don't know, I mean, like, you know, when you, yes, if you will, because we can talk offline, but it is known, right, that the way you estimate the parameters and the way you estimate kind of the support, I'm not getting into it. Ordering and size of strength of edges will matter at some point. I mean, the strength of the edges will influence the ordering somehow. So you have something which is like, well, which says it doesn't, it's very surprising.
Yeah.
I'm
well,
just saying, but
so in this regime, this won't quite shrink to 0, right?
right, okay, yeah.
So
No,
there will
but
always be a small set.
I believe what you say, but I think a fine analysis would be like, for what sizes, like there has to be a threshold of the strength of the signal, if you will.
Yes.
That is the edge strength, right?
Yeah,
That comes into play here that I can.
Yeah. So we have so for the goodness of fit test, we have a power analysis that shows there's some notion of size of signal strength, which is like there's an edge strength, but also there's
More,
a few
there
other
has to
things.
be more there, yes, no,
Mhm.
but thank you, no, this is it.
And we can show that as long as that signal strength is of order p over n, which is going to 0, then we have power 1 to 1. Okay, so just to kind of briefly wrap up here. So I told you that we could do sizes of size up to 13. This is what so on this horizontal axis, I'm showing you the number of nodes that I'm considering, and on the vertical axis, I'm showing you time. So for p equals 13, we can compute these confidence sets in about 4,000 seconds. So not fast, but something that you can do. Okay, so I'll briefly say, if we go back to this protein regulatory network, which I showed you at the very beginning, which is the Sachs et al. Data. So p is equal to 11, n is equal to 853 here. If we calculate a confidence set using the linear structural equation model setup, we actually get an empty confidence set. Right? And so the implication here is that the linear structural equation model is actually not the right model for this data. Right? And you might, this may not be so surprising, right? Because this is a very complex system. Why is a linear model correct, right? And not to say people don't use it, not to say that it's not useful, but we can at least show that the identifying assumptions are not correct. Okay, so if we model these structural equations, instead of allowing them to be linear, if we model them with cubic splines, so I told you that our theory also works if you consider the nonlinear case, we actually get something that contains the ground truth, and it's not super powerful. It still contains roughly 37% of all the orderings, but it at least seems to be doing the right thing in a pretty complex setting. Okay, so I'm going to quickly end with some benefits and some discussion here. So this is, in some sense, as far as I know, this is the first kind of way of thinking about uncertainty over causal discovery, causal models. So this, I do think this is like kind of maybe a first step, right? There are a lot of kind of things that are not perfect about this way to think about confidence sets for causal discovery, but there are some nice things. It's computationally feasible for, I'm going to say, medium-sized graphs. It allows the practitioners to see whether the identifying assumptions they use are reasonable, and it allows them to see what orderings are not ruled out by the data. The drawbacks, right? There is just an intrinsic computational bottleneck, right? This largely comes from the fact, well, I think kind of one of the interesting questions to think about is, if you think about the scalar case where you have a scalar parameter, there is like some sort of intrinsic ordering, right, to your space. In causal graphs, there's not necessarily an intrinsic ordering, so you can't just get an upper bound and a lower bound, right? So I think there's some interesting questions to think about as to what is the natural kind of, is there a natural kind of ordering to causal graphs? And there are distances and metrics over graphs, but in some ways they're a little bit unsatisfying, at least for us. And so I think there's I think there's a lot of open questions in that area. Yeah, so future work, can we think about confidence sets extended to different models? And then finally, can we think of different notions of confidence sets which don't have this computational model? Okay, so that is all I have for today. So thank you for sticking around late on a Friday afternoon. Appreciate it.
We're at time and have had some questions along the way. What I will suggest is there's refreshments waiting in the cam space, and let's have any additional questions offline. Thanks, Sam, again.